Welcome to the deep dive. We're here to cut through the complexity, break down the big topics, and give you the essential insights you need. Today, we're plunging right into a really exciting space, one that's, moving fast from just theory to actual reality. We're talking about the quantum frontier, applications and industry trends in 2025. So our mission today is basically to give you a clear, comprehensive Q&A overview. What is quantum computing actually doing right now, mid-2025? Where's the industry headed? And, what does it all mean for you? We'll be tackling some key questions, like what's the real state of practical quantum applications today? Where are we seeing the most immediate promise? Things like drug discovery, maybe AI. What about this ionq era we keep hearing about? What are the challenges and also the opportunities there? And who are the big companies, the major players driving this? What kind of hardware are they actually building? And then looking further out, what's the ultimate goal? This idea of fault-tolerant quantum computing. So yeah, if you're curious about how this pretty mind-bending concept is stepping into the real world, you're in the right place. This deep dive is all about getting a handle on the when, the how, and the what for of quantum's impact. And believe me, it gets really interesting. Okay, so we've talked before about the basics of quantum mechanics, those kind of weird rules governing the super small. But let's shift from theory to practice. Here we are, mid-2025. What is quantum computing actually doing? What's its current job?
Right. Well, what's really fascinating, I think, is that the industry is at this genuine inflection point. It's really moved beyond just academic papers. We're seeing tangible applications now and, frankly, intense competition between companies. We're solidly in what people call the NISQ era. That's NISQ, noisy intermediate scale quantum. You can kind of think of it like the very early days of classical computers, powerful in potential, but still a bit rough around the edges, prone to errors. So the main focus right now is figuring out how to get actual real-world value from these noisy intermediate-sized machines we have today. And the most promising areas that are emerging right now, quantum simulations, definitely, solving complex optimization problems, and this really new field of quantum machine learning.
That makes sense. The NISQ era, noisy but useful. So given that inherent noisiness, what's considered the most, let's say, natural fit, the application quantum computers seem almost built for.
Yeah, the most natural and maybe surprisingly the most near-term application is actually simulating quantum mechanics itself. I mean, the physical world at that tiny scale, molecules, materials, how chemicals react, it's all governed by these incredibly complex quantum laws. Trying to simulate that stuff on a regular classical computer is just, well, extraordinarily difficult. The complexity explodes exponentially as you add more atoms or particles. But a quantum computer, it operates using those same quantum principles. So it becomes this almost perfect tool for the job.
Like using a quantum hammer for a quantum nail, you said before.
Exactly. It speaks the same language, fundamentally.
Okay, so that's a great concept. How is that capability being used right now, say, in fields like drug discovery or materials science, where getting things right at the molecular level is everything?
Right. And these are probably the areas with the most immediate potential impact. In drug development, for example, big pharmaceutical companies are actively exploring this. They're using quantum computers, or at least quantum approaches, to simulate the really precise interaction between a potential drug molecule and, say, a target protein in your body.
Yeah.
Think about trying to fit a really complex key into an equally complex lock. Classically, you just try millions of combinations, brute force. But by calculating something called the binding energy accurately using quantum methods, they hope to pinpoint promising drug candidates much, much faster.
And that could speed things up significantly.
Potentially, yes. It could accelerate getting new medicines for diseases like cancer, Alzheimer's, maybe shave years off the discovery process. It's a huge motivator. And for material science, it's similar. Quantum computers could let scientists design totally new materials entirely in simulation. In silico, as they say. Things like high-temperature superconductors, which would be revolutionary, or designing better catalysts or materials for more efficient batteries. They can model the electronic structures with a precision that's just impossible for even the biggest classical supercomputers today.
And are they actually doing this now, simulating real molecules?
They are. As of this year, 2025, researchers are getting better and better at simulating small but, meaningful molecules. Things like lithium hydride, LEOH. They're doing it with increasing accuracy on the actual quantum hardware we have now. And that's really important. It validates that this whole approach isn't just theory anymore. It's starting to work.
That's incredible. Really drives home the practical side. But it's not just about simulating tiny things, is it? Let's talk optimization. That's another huge area. How are quantum computers being used for, say, massive logistical challenges?
Yeah, optimization's a big one. So many of the world's really tricky commercial problems, logistics problems, they boil down to optimization. It's about finding the absolute best solution out of a just mind-bogglingly huge number of possibilities.
Like the traveling salesperson problem.
Exactly like that, the classic example. Finding the shortest route connecting maybe hundreds of cities. The number of possible routes becomes astronomical very quickly. So as of 2025, what companies are doing is using these hybrid quantum classical approaches.
Hybrid. Yeah.
Meaning they don't run the whole problem on a quantum computer. They figure out which parts are the absolute hardest, the most complex optimization bits, and they offload those specific parts to a quantum processor. The rest of the problem, the easier stuff, is handled by classical computers.
Makes sense. Use the right tool for the right part of the job.
Precisely. And we're seeing real results. There's a pioneering Canadian company, dwave. They've reported some really interesting use cases. For instance, working with customers like Pattison Food Group, a large grocery chain. They showed they could cut the time needed for complex logistics scheduling by up to 80%.
80%? Wow. That's not just a small improvement.
No, that's potentially transformative for how a business operates. Huge efficiency gains.
Okay, and what about finance? That's another sector that deals with massive complexity and optimization, right? How are they looking at quantum?
Absolutely. The financial sector is definitely another area that's, ripe for this. One major application everyone's looking at is portfolio optimization. So balancing expected returns against risk, but doing it across maybe thousands of different assets simultaneously. It's a classic hard optimization problem. Quantum algorithms potentially could help fund managers find a much better, a more truly optimal risk-return profile than classical methods can achieve today.
Better returns or maybe lower risk for investors.
Both, potentially. Finding that sweet spot. Another critical area is risk analysis. Quantum algorithms might offer what's called a quadratic speedup for complex Monte Carlo simulations.
Quadratic speedup. Unpack that a bit.
It basically means that as the problem gets bigger, the quantum computer gets faster at solving it at an accelerating rate compared to a classical computer. So not just twice as fast, but potentially much, much faster for large, complex problems. And these Monte Carlo simulations are used all the time in finance to model market risks, predict potential crashes, that kind of thing. Being able to run them faster and more accurately could allow for much better, more timely assessments. It could help prevent crises or spot opportunities much earlier.
That's definitely a powerful incentive for Wall Street. Okay, let's shift slightly. There's a lot of buzz around quantum and AI intersecting. What exactly is quantum machine learning, or QML? What's the idea there?
Yeah, QML is genuinely one of the most exciting, though still very early stage research areas. The core idea is to use the principles of quantum mechanics to potentially create more powerful machine learning models. And this could happen in a couple of ways. One way is using quantum computers to speed up certain parts of classical machine learning that are computationally very heavy. Things like solving huge systems of linear equations or tackling those really hard optimization tasks that often bottleneck current AI training.
So using quantum as an accelerator for existing AI.
Kind of, yeah. But the other way, which might be even more profound, is developing entirely new quantum-native algorithms, things like quantum neural networks or QNNs. The idea is that these algorithms would process data that's actually encoded in quantum states using qubits. And because of quantum phenomena like superposition and entanglement, they might be able to recognize incredibly complex patterns or correlations in data that are just, well, completely invisible to any classical algorithm, no matter how powerful.
Wow. Okay, so where are we with QML in mid-2025? Is it still mostly theoretical?
It's largely still research, but moving quickly. Right now, most practical QML is hybrid, like the optimization examples. Classical computers do a lot of the data preparation and maybe some parts of the training, while the quantum processors handle the most computationally demanding bits of running the model. But we are starting to see tangible examples pop up. There's a company called SpinQ, and apparently a subsidiary of Huaxia Bank in China. They've reported using a QNN for some kind of real-world financial decision-making task.
Really? That's significant, moving beyond just lab experiments.
It is. It suggests QML is starting that transition from pure research to potential application, even if it's still early days.
Okay, that's fascinating. Let's broaden the view now from applications to the industry itself. Who are the main companies, the key players really shaping this quantum computing landscape today?
Right? It's a really dynamic ecosystem. You've got established tech giants pouring in resources and also some very innovative specialized startups making big waves. Some of the key names you hear constantly. Definitely IBM. They've been a leader for years, focusing on universal gate-based quantum computers using superconducting qubits. And they offer pretty broad cloud access through their IBM Quantum Experience platform, which has been huge for getting researchers and even businesses involved.
Okay, IBM.
Oh, else?
Google Quantum AI is another huge player. They're also heavily invested in superconducting qubits. They famously made that quantum supremacy claim back in 2019, which really stirred things up.
Right, I remember that.
Then you have dwave systems, that Canadian company we mentioned. They took a different route, focusing on those specialized quantum annealers for optimization. ionq is a major leader in a different hardware approach. Trapped ion quantum computers, they're known for really high qubit fidelity, meaning their qubits are very accurate, and also this all-to-all connectivity.
All-to-all connected. Yeah, it means any qubit on their chip can directly interact with any other qubit. That can make it easier to run certain complex algorithms compared to systems where qubits can only talk to their nearest neighbors.
Interesting. Okay, any others?
Rigetti Computing is another important name in the superconducting space. They're known for trying to build the whole full stack, from the chips themselves right up to the cloud platform and software tools.
It sounds like a busy field. You mentioned D-Wave's different approach again. Can you elaborate a bit more on how their annealers differ from what IBM and Google are building?
Sure. If we connect it back to the big picture, D-Wave really chose a specific path. IBM, Google, Rigetti, they're mostly building what are called universal gate-based quantum computers. The goal there is a machine that can, in theory, run any quantum algorithm, much like your laptop can run any software. They're aiming for general-purpose quantum computing. D-Wave, on the other hand, builds quantum annealers. These are specialized machines. They're designed specifically to find the lowest energy state of a complex system, which turns out to be mathematically equivalent to solving certain types of optimization problems.
So less flexible, but maybe better at one specific thing.
Exactly. Think of it like a universal computer is like a programmable calculator that can do anything, while an annealer is like a specialized tool designed perfectly for just finding the minimum value in a complex landscape. So while D-Wave's machines aren't universal, their systems like the Advantage 2 have thousands of qubits now, far more than many gate-based systems. And they are being used today by commercial clients for real-world optimization tasks that classical computers struggle with. It's a different strategy targeting near-term value for specific problems.
That distinction is really helpful. It really clarifies the different philosophies, and it brings us nicely to the hardware itself. We know there's not just one way to make a qubit. What's generally considered the most mature hardware technology right now, and how does it actually work?
Yeah, the technology that's probably furthest along in terms of scale and development right now is superconducting qubits. That's the approach used by the big players like IBM, Google, and Rigetti. Basically how they work is, you create these tiny electrical circuits, like microscopic loops or junctions made out of superconducting materials. Then you have to cool them down to incredibly low temperatures, near absolute zero, colder than deep space.
Wow, why so cold?
Because at those extreme temperatures, the materials become superconducting electricity flows with zero resistance. And crucially, the circuits start to behave according to quantum mechanics. They act like artificial atoms. Just like a real atom has distinct energy levels, these circuits settle into specific energy states. You can then use two of these states, a ground state and an excited state, to represent the 0 and 1 of your qubit, and you control them using microwave pulses.
Okay, so super cold, tiny circuits acting like atoms. What are the main pros and cons of going down this superconducting route?
Well, the big advantages are speed and scalability, kind of. The gate operations flipping a qubit from 0 to 1 or making two qubits interact can be very fast, often on the order of nanoseconds, billions of operations per second. That's crucial.
Fast gates are good?
Very good. And also, the technology uses fabrication techniques that are similar to those used for making classical computer chips in semiconductor foundries. That existing expertise and infrastructure is a huge plus when you think about trying to manufacture hundreds or thousands of these things reliably.
Okay, speed and manufacturing familiarity. What are the downsides?
The main downsides are significant. These superconducting qubits are extremely sensitive to noise, tiny vibrations, stray electromagnetic fields, even temperature fluctuations. This noise causes errors and makes them lose their quantum state very quickly, a process called decoherence. So they have relatively short coherence times. That's the window you have to actually perform your computation before the quantum information is lost. It's a constant battle against noise.
Right. The N in NISQ noisy.
Exactly. And of course, there's the practical challenge of needing those huge, complex, and very expensive dilution refrigerators to keep them near absolute zero. That's a major infrastructure hurdle for building and operating these machines.
Definitely sounds like a balancing act. Okay, what about the other main approach you mentioned, trapped ions, championed by companies like ionq? How does that work, and what are its pros and cons?
Right. Trapped ions are quite different and in some ways more elegant, perhaps. The basic idea is you take individual atoms, zap them with a laser to knock off an electron so they become positively charged ions. Then you use carefully controlled electric and magnetic fields to trap these ions, holding them perfectly still, suspended in an ultra-high vacuum, like tiny charged marbles held by invisible forces.
Okay, holding individual atoms still.
Yeah. And then you use precisely tuned lasers aimed at these individual ions to manipulate their internal energy states. Different energy levels within the atom itself because of the 0 and 1 states of your qubit. You use lasers for the gate operations.
Lasers instead of microwaves. What are the advantages here?
The big pros are, firstly, fidelity and coherence. Because every ion of the same element is naturally identical, the qubits are remarkably consistent. This leads to very high fidelity, meaning the operations are very accurate, fewer errors, and they have incredibly long coherence times compared to superconducting qubits. We're talking seconds or even minutes in some lab experiments versus microseconds or milliseconds. That's a massive difference, giving you much more time to compute.
Orders of magnitude longer.
Exactly. Plus, they often feature that all-to-all connectivity we talked about, which is a big plus for algorithms.
Okay, sounds great. What are the catches, the cons?
The primary cons are speed and scaling, essentially the flip side of superconducting qubits. The gate operations using lasers are significantly slower, typically in the microsecond range rather than nanoseconds. So you can do fewer operations within the coherence time, even though that time is longer.
Slower gates.
Slower gates. And scaling up the number of ions you can effectively trap and control individually in a single trap is a major engineering challenge. Getting to hundreds or thousands of ions in one interconnected system is proving very difficult.
So it's a trade-off. Higher quality qubits, but slower operations and harder scaling, maybe?
That's a pretty good summary of the trade-offs right now, yeah.
Interesting. Okay, there's a third approach you mentioned, photonic qubits, using light. What makes that appealing, especially you noted for quantum communication, and what are the hurdles?
Right, photonics. This approach, pursued by companies like Xanadu in Canada, is different again. It encodes the quantum information, the qubits, into the properties of single photons, individual particles of light. This could be their polarization or their timing or path.
Qubits made of light particles.
Essentially, yes. The biggest advantage, arguably, is that photons are naturally very resistant to decoherence. They don't interact much with their environment, so they can hold their quantum state for a long time. And they can travel easily over long distances through existing optical fibers with very little loss. This makes them almost ideal for quantum communication, sending quantum information securely between locations, maybe building a quantum internet.
That makes intuitive sense. Light travels well. Any other pros?
Another practical plus is that photonic quantum computing hardware can often operate at room temperature, which gets rid of the need for those massive, expensive cryogenic systems. That's a huge potential advantage for deployment.
Room temperature quantum computing. That sounds appealing. What are the challenges then?
The main challenges are pretty fundamental. First, reliably creating single photons on demand and then detecting them efficiently is technically difficult. You need perfect single photons, not faint laser pulses. And perhaps the biggest hurdle is getting photons to interact with each other. Photons naturally just pass right through each other. But for quantum computing, you need qubits to interact to perform essential two-qubit gates. Making photons talk to each other strongly and reliably is a major focus of research.
Right, you need them to influence each other to compute. Okay, that's a great overview of the main hardware contenders. So let's try to wrap things up a bit. Summarizing the state of the quantum frontier in mid-2025. What's the industry's main focus right now, and where are the most promising applications we're seeing today?
Okay, yeah. So as of 2025, the quantum computing industry is absolutely firmly in this NISQ era, noisy intermediate-scale quantum. The primary focus, therefore, isn't yet on building massive, perfectly error-corrected machines. It's really about finding clever ways to extract real-world, tangible value from the imperfect, error-prone, medium-sized machines we have today. It's about practical utility now.
Making the most of what we have.
Exactly. And the most promising application areas where we're seeing traction are, first, quantum simulations. These seem poised to deliver genuine breakthroughs in chemistry and materials science. Think drug discovery, designing better catalysts, new battery materials. That's very near-term potential. Second, solving complex optimization problems, especially in finance and logistics, using those hybrid quantum classical approaches. We're seeing actual efficiency gains being reported there. And third, exploring that fascinating synergy between AI and quantum systems, QML, trying to find ways quantum can enhance machine learning for better data analysis and pattern recognition. That's maybe a further out, but incredibly exciting.
That's a clear picture. But looking ahead, the industry isn't just stopping at NISQ, right? You hear roadmaps like Google's aiming explicitly for a fault-tolerant quantum computer by, say, 2029. What does that long-term goal signify for the field? Why is fault-tolerant the ultimate prize?
Right. That focus, that explicit long-term goal from major players like Google is hugely significant. It signals a major strategic direction for the whole industry. Because while all this current work in the NISQ era is vital finding uses for today's noisy processors, the ultimate dream, the real game changer, is a machine that can run any large-scale quantum algorithm without being constantly derailed by errors.
Algorithms like Shor's, the one that can break encryption.
Exactly. Shor's algorithm is the famous example, but there are many others for simulation, optimization, and tasks we haven't even conceived of yet that require millions or billions of operations. NISQ machines simply can't handle that complexity due to noise. So achieving fault tolerance means implementing quantum error correction. It means figuring out how to use many unreliable physical qubits to encode a single, stable, effectively error-free logical qubit.
Building robustness out of noisy parts.
Precisely. It's an enormous engineering and scientific challenge, but it's seen as the absolutely necessary next step. It's the key that unlocks the full, potentially world-changing power of quantum computing. Moving beyond these specific near-term applications to tackling problems that are utterly intractable today. It signifies the transition from specialized tools to potentially paradigm-shifting supercomputers in the next decade or so.
What an incredible journey we've been on today. A real deep dive into the quantum frontier. We've covered so much ground, how that theoretical promise is really starting to turn into practical applications. We've seen it in drug discovery, materials science, logistics, finance, even AI. And we've mapped out the key companies involved and dug into the fascinating different ways they're trying to actually build these machines, superconducting, trapped ions, photonics. It's quite a race. It's clear the quantum frontier is wide open, and the exploration is definitely picking up speed. So the question maybe for you, our listener, is, what will you explore next in this field? How might quantum touch your industry? What breakthrough might be just around the corner? Lots to think about.
Well, thank you so much for joining us on this deep dive into the quantum frontier today. If you found this useful, if you want to keep getting this kind of knowledge quick but thorough, definitely subscribe to our channel, Tech AI and Beyond. We'll be back soon with another deep dive, breaking down another complex topic just for you.